Hello everyone, Kotungwane the Native God here. Right, now today we will be looking at a very interesting topic called kinematics. Right, now we'll be looking at kinematics from the perspective of Mechanotechnics N6. We also do cover kinematics in engineering science N4. So if that's what you're looking for, you can stop the video right now and check on my playlist, and you should see videos relevant to kinematics, right? But if you're looking for kinematics for Mechanotechnics N6, you are in the right place, right? Now, kinematics is essentially a branch of mechanics where we look at the, say, definite relative motion of objects without really having looked at or without referring to the forces responsible for causing the motion, right? We will particularly look at kinematics of machines or mechanisms, which essentially deals with the study of relative motion of machine parts, right? Now, before we get started, let us look at what a mechanism is, right? How do we define mechanism, right? Now, there's many ways we can define mechanisms, right? But essentially all it is a combination of rigid bodies so shaped and connected that they move about each other with definite relative motion, right? Now, I'm going to demonstrate what I mean by this definition, right? But before I do so, let's have a look at types of motion, right? It's very important that we know and understand the types of motion that we can expect under kinematics or under mechanisms, right? Now, the reason for that is that a mechanism is essentially comprised or composed of components, right? The components of a mechanism are known as kinematic link, or just a link, or even elements, right? So if I refer to any of those terms, I'll be referring to some component of a mechanism, right? So I'll probably be using kinematic link the most, right? Now, a mechanism is composed of links, right? Links can either be fixed, links can also be in motion, right? So you have links that are fixed and you have links that are able to move, right? Now, of the links that are able to be in motion, right, the kinematic links that are able to be in motion will move in one of three ways, right? One being translation, right? Now, translation is also known as linear motion, right? The second being rotation, right, which is also known as angular motion, and the third one being a combination of essentially translation and rotation, right? So a kinematic link will either translate, or it will rotate, or it will move in a way that it combines both translation and rotation, right? That is why it is important to be familiar with these types of motion, right? Because essentially the kinematic links will move such that they'll either translate, rotate, or translate and rotate, right? Right. Now, in demonstrating what essentially a mechanism does, or what a mechanism is, right, let's consider this slider crank mechanism, right? Now, you have different types of mechanisms, right? I'm not really going to get into the types of mechanisms. There's many of them, right? The one we are looking at right now is known as a slider. So this is a slider crank mechanism, right? This is a slider crank mechanism, right? Now, this mechanism in particular has the following components, right? You have the crank, you have the connecting rod, and then you have the slider, right? Now, what I said was in a mechanism you get, or a mechanism is comprised of kinematic links, right? Some of the links will be fixed, right? And some will be in motion, right? Now, if you look here, if you look at our slider, right? So here's our slider. Our slider normally moves within what we can refer to as guardrails, right? So call this, we can refer to this maybe as, what is guard rails, right? Now guardrails are fixed, right? Guardrails are fixed, so we can take guardrails as being fixed, right? Also, this point is fixed, right? The point referred to as the frame here, right? Also, you can refer to the guardrails as the frame as well, right? Now, as far as the number of kinematic links of a certain mechanism, right? Now, in this case, we're looking at a slider crank mechanism. The fixed links, right? So any and all fixed links you take as one, right? So on this slider crank mechanism, you have this frame as well as the guardrails, this frame, right? So that's two fixed links. Those two fixed links you take as one, right? So in terms of how many kinematic links we have on this slider crank mechanism, right? You have the frame, right? Or you have the fixed links, which you take as one. And then second, you have the driver link, which we can also refer to as the crank, right? So that's number two. The third link will be this connecting rod, right? The connecting rod connecting the crank with the slider, right? And then the fourth one will be the slider itself, right? Very important information, right? Very important. So again, any and all fixed points, right, you take as one. That's going to be important in drawing the velocity diagram, but we'll get there, right? Now, let me demonstrate how these kinematic links move relative to each other, right? So this is a schematic of the slider crank mechanism, right? So this here is the schematic of the slider crank mechanism, right? Now you have links that are fixed, right? And then you have links that are able to be in motion, right? Now what tends to happen is you have the crank, or you have the driver link. Our crank here is OA, right? Our crank here is OA. AB is our connecting rod. B itself is the slider, right? And then O1 and O2 represents the fixed link, right? So remember, the fixed link here is frame 1, right? Frame 1. And then this fixed link, right, is not labeled, right, as a fixed link, but it is important to note that this here, the guardrails, or this frame, is also a fixed link. Again, it is going to be important to note that in having to draw the velocity diagram when we get to that, right? So essentially O1 and O2 represents, so O1 and O2 represent the fixed links, right? And then we have OA, which is our crank or driver link. You have AB, which is the connecting rod, right? And then you have the slider B, right? Now, in a mechanism, or let me speak about the one we have in front of us, right? Now, on this mechanism, right, the slider crank mechanism, only one of these links is rotating, right? You have the crank or driver link. That is the one that is going to be rotating, right? So in terms of the kind of motion that we can expect our crank to have, right, it is rotation. So this one will essentially be doing this here, right? This one will be rotating, right? So it rotates. Now, how does the rotation of the crank influence the connecting rod, right? That is where the definition of mechanism comes from, right? How does the motion or the rotation of the crank influence the connecting rod, right? So essentially, how does OA rotating influence AB, right? Now, when the crank rotates, right, say it's going to rotate clockwise, right? So say this is rotating clockwise. How does this rotating clockwise influence our connecting rod, right? Now, when the crank rotates clockwise, what tends to happen, or what would tend to happen to the connecting rod, right, is the connecting rod is essentially going to have a combination of what? Translation as well as rotation, right? Remember, translation is essentially linear motion being motion in a straight line, essentially, right? So it's going to have a combination of translation and rotation, right? So meaning, in order for there to be some kind of translation, right, the connecting rod also has to rotate, right? So if the crank rotates clockwise, what will essentially happen is that the crank is going to somewhat pull the connecting rod. So pulling the connecting rod, meaning it will go in this direction, right? Now, when this rotates essentially anti-clockwise, so if you look at the direction of rotation here, if this is being pulled, right, so it means essentially it will be rotating anti-clockwise, right? Now, the rotation of this going clockwise influences what? Influences the slider, right? So for the slider to move, this has to rotate, and in rotation, it also what? Translates. So essentially it does that. So it translates, and when it translates, it essentially pushes, right? It pushes the slider B in that direction, right? And then slider B will translate, right? So slider B only translates, meaning it moves in a straight line, right? Now, seeing that the slider B is horizontal, it means that the motion about slider B will either go to the right or to the left, or will either go to the positive X direction or negative X direction, right? And yeah, that is how mechanisms works. That is how mechanisms work essentially, right? They move upon each other based on how they are shaped and connected. They move upon each other with relative motion, right? So that is what it means, right? So that is what that definition means, right? Now, this is not particular to the slider crank mechanism, right? It applies to any and all mechanisms, right? I just used the slider crank mechanism because that's the most common one, right? Right. Now, regarding the sections we cover under kinematics, right? These are the sections we are going to cover under kinematics, right? Methods of velocity analysis, right? Now, under methods of velocity analysis, we are going to use, or we are going to be looking at these subsections. So the velocity diagram, as well as the eye-center method. So we are going to use the velocity diagram as well as the eye-center method, right, in determining the velocity of the links, right? Whether the link is rotating, so whether the link is rotating or translating, or if the link rotates as well as translates, right? We're going to be using these two methods in analyzing the velocity of each link, right? And then the second section, right, we will be analyzing the acceleration of the links, right? And we will do that using the acceleration diagram, right? Now, in both these sections, so the method of velocity analysis as well as the methods of acceleration analysis. In both these methods, we are also going to make use of what we call space diagram, right? So in both methods, we are going to make use of the space diagram, right? In fact, before having to draw the velocity diagram as well as the acceleration diagram, we must first draw the space diagram, right? So we're going to use both methods in conjunction with the space diagram, right? All of that is going to make sense when we start looking at some examples, right? Right. So yeah, that is what you can expect to learn from kinematics on this channel, right? Now, looking at the kinds of velocity or the types of velocities that we can expect to determine, right, in kinematics, right? Now, for a link that is only translating, or for a link that only translates, so a link that is in linear motion, right, you can only determine the radial velocity, right? Or let me just say the linear velocity, right? So meaning looking at this slider crank mechanism, right, we have the slider B, right? The slider B, right, only translates. So meaning that as far as the velocity analysis of the slider, we are only going to determine the linear velocity or radial velocity of the slider, right? Now, links that rotate, right? Whether the link is just rotating or the link has a combination or does a combination of rotation and translation. As long as there is some rotation that a link does, right, we will only consider what we call tangential velocity, right? We are going to consider what we call tangential velocity, right? We are going to consider the tangential velocity of that link, right? So if a link is rotating, then we're only going to look at its tangential velocity, right? Remember, if you have a rotating body, right? If you have a rotating body, say you have a rotating body, right? Right, so you have a rotating body, right? So this goes, say this is rotating in that direction, right? That is rotating in that direction, and you have, say, the radius at that point, right? In order to be able to determine the tangential velocity or the velocity of this rotating body, right, we consider the tangential velocity, right? So this would be the tangential velocity, right? Tangential meaning tangent, right? So this velocity is tangent to essentially the circle, right? So this would be, let's call this tangential, let's call it VT, right? So this would be the tangential velocity of this rotating body, right? Now if you look here, if looking at the rotating body from the perspective of its radius, right, if we look at it from the perspective of its radius, the tangential velocity would be what? Would be perpendicular to the radius, right? Again, if we look at the rotating body from the perspective of its radius, right, the tangential velocity would be perpendicular to the radius of the rotating body, right? Now, what does this tell us regarding the links or the rotating links on a mechanism, right? if we have to calculate the velocity of a rotating link, then we have to find its tangential velocity. Now, its tangential velocity will be perpendicular to the link. Why perpendicular to the link? The link, right? The link represents the radius of the link, right? So to get the radius of this link, right? The radius of this link is its length, right? So each of these links, essentially, we are able to take as the radius of the link itself, right? So meaning that, seeing that we've established that the tangential velocity will be perpendicular to the radius, right, of the rotating body. Now, the radius of each link is its length, meaning that to get, for instance, the tangential velocity of the crank OA, right, we would have to get, or we would have to draw a line that is perpendicular to the link OA, right? Now for this instance, right, also I forgot to mention that how we look at, or how we analyze the velocity of the links, right, is by looking at them at the instant that the crank is at a certain angle. Like for instance, this crank here in this instant is at an angle of 60 degrees, right? So we then analyze what the velocities of these links are relative to each other when the crank is at 60 degrees, right, from the x-axis, right? Now, taking that into consideration, right, when having to determine the tangential velocity of crank OA, right, we've established that that crank has to be at 90 degrees with, or must make 90 degrees with the line that you're going to draw that represents the tangential velocity, right? Now, I'm going to measure here 150. I'm going to measure 150, right? Now, if we draw a line here, right, if we draw a line, right, now this line being perpendicular to the link, right, this line being perpendicular to the link represents, let's make this dotted, right? So the dotted line represents, right, how we would draw, how we would draw in the direction as well of the tangential velocity of the crank OA, right? So the direction is such that it corresponds with how the crank is rotating, right? Remember I said the crank is rotating clockwise. So if the crank is rotating clockwise, its tangential velocity will point in that direction, right? Perpendicular to the link, right? Now for any and all links that rotate, right, whether it is just rotating or does a combination of both rotation and translation, right, the velocity that we analyze will be its tangential velocity, right? And we get its tangential velocity by essentially drawing a line that is perpendicular to the link, right? Now that was just a breakdown of what you can expect as far as the first section being methods of velocity analysis, right, using the velocity diagram, right? Now we are going to draw a velocity diagram when we look at an example on kinematics, right? Right now though, I just want you to go over what we covered here, right? Try to understand it, because essentially this is pretty much all you need to understand this is all you need to understand in order to be able to do problems based on the analysis of velocity using a velocity diagram, right? As far as the Eisenhower method, that I will cover later, right? For now, right, in the next couple of videos, I'll be focusing on the approach we take in drawing the velocity diagram, right? By the way, this here, right, is the space diagram for this particular slider crank mechanism, right? Now from this, we would then draw the velocity diagram, right? Now, maybe just a quick one before I end the video, right? Now, in drawing the velocity diagram, right? In drawing the velocity diagram, right, you are going to need set squares, right? You're going to need 2 set squares, the 60 and 45, right? If you can get the roller scale as well, you can get the roller scale. The roller scale in particular is going to be important for drawing the acceleration diagram, right? But as far as the velocity diagram, you need 2 set squares, right? And of course, you need a protractor as well as a compass, right? And then you'll be good to go, right? Right. I hope this video was helpful to you, right? I hope you enjoyed going through it as much as I enjoyed doing it, right? Hopefully you enjoy kinematics. Kinematics is very interesting. I like it very much, right? So hopefully I'll be able to impart the knowledge that I have regarding kinematics, and that it will help you in your assessments, be it your summative assessments or your final exam, right? All right. Please hit the like button. If you haven't subscribed, subscribe to the channel, and also hit the notification bell so that you don't miss out on any other content that might be helpful to you, right? Also refer me to your classmates, right? I believe this will also be helpful to them, right? Okay. Nated God signing out.